Good afternoon. I have a few notes and then I'll launch into the presentation. First of all, I'd like to thank Alan, Becky, Stuart, and the other moderators, and Dean Whitlaw for putting together such a wonderful conference. One of the things that has been especially useful is ample time for discussion with presenters after the presentations. Used to getting mauled during presentations, so that's kind of nice. But at the same time, it's important that you do push back, and there's a lot to push back on in this presentation, so I'd like to encourage you to beat me up after the presentation. It's fun. I'd like to, let's see, I'm going to back up here. Where are we? Oh, okay, that's the one on the left. I get it. I'd like to acknowledge some people who supplied data. Resource management is run by a company, by a guy named Dana Slaymaker. He has an UltraCam type camera, and I'll be showing you some pictures from it. In his rendition, there are 30, 60 megapixel cameras taking photos as planes and drones move forward. His problem is too much data to look at after a flight. And you'll see why in a few minutes. He's doing survey-related work in the Gobi Desert. The data I'll show you is from Caribou in Alaska. I'd also like to thank Shell Oil. And they're the people we've been working with most closely on data during the last year of the kind that I'll be presenting. They have a more operational problem. Well, first of all, they're required by NOAA and NIML to do marine mammal surveys, marine mammal mitigation surveys, in order to get drilling permits. Secondly, and more interestingly, from a real-time decision-making viewpoint, as their ships do seismic testing, moving along the water at 4 or 5 knots, they and other oil companies are required, increasingly, to do a scan of the nearby water to see if there are endangered whales and walrus. Those are usually the two most endangered animals they're concerned about. And if, in fact, there is one found, then increasingly requirements are that they don't make noise. And as most of you know, the similar requirements are squeezing navies from doing active sonar testing for anti-submarine warfare. So there's a kind of a real-time or almost real-time action component associated with this, and that's kind of what I'd like to focus on. The customer and co-authors for this paper are from a company called LGL. LGL must analyze the data for Shell Oil, some of the data that we'll be talking about. And along the way, it takes so much time for them to analyze the data that they came to us and said, is there some way that you can speed it up automatically? So what's all this got to do with drones? Well, the data that we'll be talking about came from manned aircraft. Each of these end users and many others are interested in transitioning from manned aircraft to drones. And the nice thing about both of them is that they have available data now. They have an immediate problem now to solve. And in the process of talking with them, learning about them, delivering a product to them, we are poised now to put the processes that we've delivered for very rapid post-flight analysis onto drones. And as a result, they've been kind of ideal customers. So briefly, I'm going to, this is a quick outline, I'm going to go through a wildlife detection scenario and look at some slides with you. And after that, we'll get into the value proposition associated with the automatic or semi-automatic detection of events. and then get into some of the operational prospects, the kind of monetizing the value. And I don't know whether there'll be time to peek under the hood, but if there is, I'll say one or two things about that. Okay, well, this is one of Dana's images. It's a stitched rendition of 30, 60 megapixel images taken from an aircraft at 1,500 feet above altitude. And there's some caribou in there. And you can all see that there are 28 caribou in that picture, right? Well, maybe not. So Dana said, you know, I'm going to take a whole bunch of these pictures, and it's going to take forever, about an hour per image, for people to zoom in on them with Photoshop or the like, and actually look for these guys. So what we said to him was, well, suppose you looked at and we call them chips, VGA-sized, full resolution subset of these images. Suppose you looked at these at a rate of about 1 per second. Would it help? And he said, well, yeah, it would help a lot, because in a typical picture, there are none to 20 or 30 caribou. These are caribou from Alaska in these pictures. So we said, yeah, we can do that. And further, we said, well, suppose you looked at each one of these things, 1 per second in a rendering. Would that help more? And he said, yeah, it would help. We went on to say, you know, we're going to show you a lot of these snapshots, and maybe 1 in 20 is going to actually have a caribou in it. The rest are going to have false alarms. Do you think you could blow through those quickly enough so that you'd actually save a lot of time and effort, assuming that we'd pick up most of, we'd show most, if not all of them? He said yes. This is where we found the caribou in this picture. Nearly all of them were there. There were a few in other areas. And this is what we call an alert map. So besides delivering these chips at a rate of 1 per second, what we do is to deliver a circle around each of them. And we also show where the false alerts are. Pretty much along that ravine down on the bottom there, they were all false alerts. Okay? So there is a delivery of quite a few false alerts, but the overall value in terms of reducing manual analysis effort is substantial. And if you're at a point where you want something like this on a drone, which we do eventually, then there's a huge reduction in telemetry. Instead of sending these enormous images in full resolution, you send just these chips, which are a huge subset of, is there such a thing as a huge subset? Which is a major subset of the telemetry and the bandwidth. All right, so this is the other application, and this is the one that we looked at very closely. These results were presented in Fairbanks at a UAS group meeting a few weeks ago, and they'll be presented in a lot more detail at the UAS Commercialization Expo next week, and in San Francisco at the Marine Mammal Science meeting in December. Can you see the whales in these pictures? Oh, I guess you can't. That was a trick question. Thank you. Somebody's looking at the slides. Great. So, can you see the whales in these pictures? Imagine that you have to look at them at a rate of 1 per second. 10,000 of these pictures come from one flight. It takes a one-person year, marine biologist, master's level person year, to drill down on these images so that you can see them after a flight. Our customer said, here's the spec. We would like to blow through these pictures at the rate of 1 per second. That way, we're going to be able to take action if, in fact, there's a whale in them. So what we delivered again were some chips And this is what the chips look like. And in these chips, and these are a little bit misleading because in an array of 15 chips like this, you might see one whale. And you might see 10 arrays like this before you see one whale, but this is kind of what it looks like. And in these, there were a lot of false alerts due to glint, and there were many more false alerts due to whitecaps. But they said, yeah, we like it. It saves us a lot of time. And if you're on board an aircraft with it, it saves a lot of telemetry. These are some close-ups, and this is the way that we're looking at them. They're looking at them, actually. We're delivering one of these chips in full resolution every second for them to look at. And when they see something, they need to take a little time to log it and figure out where it is and so on. And here is the alert map that we deliver when, in fact, we find something on an image. 99% of the images have nothing of interest. So we got a very nice endorsement from the customer. And this will just give you a sense of what happens. Let's keep in mind, please, that there's always a person in the loop. And everything that I've ever been associated with image processing, I've never seen a case where you did not need a person in the loop, at this level of precision. So the overall detection rate was 70% to 100%. The time, there were a lot of false alarms, but key here was the amount of time that it took these folks to analyze the data. And when we fast forward to real-time applications on board an aircraft, that translates into bandwidth. Okay, just like to talk next about kind of monetizing value and in the process showing where the bottlenecks are, the value bottlenecks are in this kind of a setting. Here's a spreadsheet. There's a great Hawaiian beer advertisement that we see in San Diego. It goes something like this. There's only one happy hour per day, typically. We think it ought to go the other way around. There should only be one sad hour per day. And during that sad hour, somebody may have to look at or build a spreadsheet. The other 23 hours should be happy hours. That's the way the advertisement goes. And of course, they're drinking beer and having fun during the happy hours. So in this spreadsheet, what we did in green was to put in some input metrics. And they include the resolution, the focal length of the camera, the height, the altitude at which the bird is flying. And this is actually consistent with what Shell Oil did in 2012 with their D800 cameras flying from sea otters, twin otters. Every second, a camera that was tilted on the left and on the right took a picture. So there was some overlap. And it was a D800 camera, 4912 by 7360, and flying at 305 meters, this and that. The red is kind of the output of this spreadsheet. Also included on the input is that it was taking 10 minutes per analyst to look at the images. And what comes out is that instead of 60-person weeks to look at the images from one flight, it was more like 4-person hours. We like that number because that means at the end of a flight in Barrow or on a ranch, somebody can look at the data and say, oh, tomorrow I need to avoid these marine mammals, or I need to go find my Kobe beef that's strayed in South America, that kind of a thing. Another interesting aspect of this, as far as an input metric, is the transmission upload rate. 25 megabits per second is what Cox offers commercially in Southern California, in Nevada. At that rate, if you wanted to upload all of this data for analysis to the cloud from one flight, it would take, where's that number? 69 hours. So the idea of getting data uploaded and crunching it to pieces on the cloud is pretty ambitious. You need to do the processing near the sense data. And ideally, you need to do it on the plane. And even more ideally, you need to do it on the UAV, or else it's never going to get looked at, or it's going to take forever to look at. So this is another way of looking at things that we're bringing to customers, and we're saying, you know, does this make sense? The model here is a ranch in South America where somebody is flying a drone, taking 1,000 high-resolution pictures per day, and as a result, they're looking at 365,000 images per year. And according to the story, and we're kind of working this out with a customer, there might be, every day there might be one stray Kobe beef that they're trying to find. And if in fact they send somebody out to look for this animal or to take some action, it might cost $100 per event. But if in fact they don't find this animal, if it's been poached or killed or strayed off somewhere, it's going to cost a lot of money, $10,000 off the hoof. So in a one scenario where you're doing some automated detection, you can have more detections and fewer false alerts than in the other. So if you turn the crank on this, there's potentially a large saving through this automated analysis. And as some of you know, there's a kind of a spreadsheet and a statistical decision theory basis for all of this. But that's the story. So I think I'll kind of wind it down at this point and go into a little bit on the operational side. Right now, we're delivering, and we have delivered, a product in a box where at the end of a flight, you deliver 10,000 images to the box, and out comes these chips. That's what we're doing now, after a flight. The ultimate goal is to have this on a bird and have the processing going on the bird so that the operator down on the ground can be getting these chips in real time so that they can take action. And I'll be happy to go into more detail about that. We're going to skip the peek under the hood, but I'll be outside and we can go through all this stuff in detail. But in summary, what I've tried to do is just to give a scenario of the kind of detection that we're looking at from aboard aircraft, and pretty soon drones. We're kind of practicing our steps in the bathroom before getting out on the floor. I've gone through a few added value analysis examples and some operational prospects. And again, I'd be happy to peek under the hood with anyone who's interested during the next break. And that's it.